All right, let's get into it. Today we're going to talk about one of the true unsung heroes of our digital world. Seriously, it's a piece of technology so fundamental that you're using it this very second, but I bet you've never heard its name. We're going to do a deep dive into the code that basically conquered digital noise.
I mean, really think about it for a second. How is it that your Wi-Fi is so incredibly stable, or that your Netflix stream just works without constantly glitching out? You're sending and receiving billions of bits of information through the air, through cables, with all sorts of interference all around. How does it all get there perfectly? Well, the answer is that every single one of those bits is in a constant battle against an invisible enemy we call noise. Could be radio interference, could be a tiny little flaw on a hard drive. Anything that tries to flip a 1 into a 0 or a 0 into a 1. The secret to winning this fight is a really, really smart error-correcting code.
So here's how we're going to break it down. We'll start with the big picture, the quest for perfect data. Then we'll meet the code that gets us unbelievably close to perfect. We'll see how it works its magic, where we're using it today, and finally, we'll look at the last tiny frontier that's left to conquer.
Okay, first up, let's set the stage. We need to understand the fundamental challenge here, which is this quest for perfect communication in what is a very, very noisy world.
Way back in the 1940s, this absolute genius named Claude Shannon figured out the universe's speed limit for information. He calculated the absolute fastest you could send data down any channel, like a radio wave or a copper wire, and still be able to fix every single error. This became known as the Shannon limit, and for information theory, it was the holy grail. For decades, though, it was just that, a beautiful theory. Getting anywhere close to it in the real world, it seemed totally impossible. But then a new hero entered the scene. A technology that could get us so incredibly, almost unbelievably close to that perfect speed limit.
And they have a name, Low-Density Parity-Check codes, or as everyone calls them, LDPCs. And their performance? Well, it's nothing short of near optimal. These are the codes that finally let us knock on the door of Shannon's theoretical dream.
Now this is where the story gets really wild. A guy named Robert Gallagher invented these codes way back in 1963 for his PhD thesis. But here's the kicker. The computers back then were nowhere near powerful enough to actually use them. So this brilliant world-changing invention, it just sat on a shelf, ignored for more than 30 years. It wasn't until the mid-90s when computers finally got fast enough that it was rediscovered and boom, it became the superstar of our modern digital world.
So what's the secret sauce? What makes these LDPC codes so incredibly powerful that they were literally 30 years ahead of their time? Well, the biggest clue is right there in the name.
It all comes down to those first two words, low density, or to put it another way, sparse. You see, at its heart, an LDPC code is basically a set of mathematical rules, or checks, that are defined by a grid of ones and zeros called a matrix. And the absolute magic of it is that this matrix is mostly empty.
Right. So older codes were built on what you'd call dense matrices. Think of a super tangled web of connections. Trying to find an error in that mess takes a ton of computing power. But LDPC codes, they use a sparse matrix. It's more like a clean, simple blueprint with just a few connections. And that makes the problem of finding errors way, way easier and faster to solve.
And it's so important to get this. That simplicity, that sparsity, it's not a weakness at all. It is the entire secret to their incredible speed and power. It's the whole ballgame.
Okay, so we've got this sparse blueprint. How does that actually help us find and fix a tiny error in a stream of billions of bits flying through the air? It uses this really clever process called iterative decoding. The best way to think about it is like a team of detectives working a case. So the data comes in, maybe with an error. Each check from that sparse matrix looks at just a small group of bits. If a rule is broken, it sends out a message to the other checks, kind of like a vote, saying, hey, I think this bit over here is wrong. The other checks get those messages. They update their own beliefs, and they pass new messages back. This happens over and over, back and forth, and in a flash, all the detectives reach a consensus on exactly where the error is, and they flip it back to the right value. Case closed.
And the results? They really do speak for themselves. You can see here, the data shows time and again that across all kinds of noise levels, LDPC codes just blow older standards out of the water. It's not just a little better, it's a massive leap forward, getting us right up to that near-optimal performance we were talking about.
So, now that we know how this brilliant tech works, where can you actually find it? Well, the short answer is just about everywhere you look.
That Wi-Fi signal you're probably on right now? Yep, protected by LDPC codes. The 5G connection on your phone? You guessed it, LDPC. The signals coming back from probes in deep space, digital television, the data stored on your solid-state drive, it is the foundational tech making sure all that data is clean. It's even being looked at for crazy futuristic stuff like protecting fragile quantum computers from making mistakes.
So LDPC codes are almost perfect. They get us right to the doorstep of the Shannon limit. But there is one last, tiny little challenge that the smartest engineers in the world are still trying to crack.
It's this weird phenomenon known as the error floor. What happens is, at very, very low error rates, I'm talking like one bad bit in many billions, the performance of some LDPC codes can just suddenly plateau. It hits a floor that it just can't seem to break through.
And this happens because of some very rare, specific patterns in the code that can create something called low-weight code words. You can think of these as clever disguises for errors. They can sometimes fool that team of detectives, creating a really stubborn error that's super hard to fix. It's this tiny, tiny imperfection in an otherwise brilliant system.
But let's be really clear here. While they aren't 100% perfect, they get us so incredibly close. They deliver the rock-solid reliability that our modern digital lives absolutely depend on. They are the reason we can stream and download and communicate with a clarity that would have seemed like pure science fiction just a couple of decades ago. So when you put it all together, we have pushed right up against the absolute theoretical limits of communication. The work of Robert Gallagher, once lost to time, now underpins our entire connected world. And it leaves us with this one fascinating question. In this relentless quest for perfection, can we ever find a way to eliminate that last, final, tiny fraction of an error and finally achieve Shannon's perfect dream?